Hall effect. Now let's look at the picture here. Okay, so first of all, you have this brown color piece of stuff. What is this? This is actually a probe. A probe. Huh? So what is meant by a probe? You can see here, a probe. So a probe is actually what is a semiconductor. Okay, it's a semiconductor. Huh? So this piece of brown color material is a semiconductor. Semiconductor. Huh? Okay, so you have this semiconductor here. Then you make a current passes through the semiconductor and then come out on the other side of the semiconductor. So what happened is, at the meantime, when the current pass through the semiconductor, you have a permanent magnet that starts from the bottom, which means the North Pole is at the bottom, and then you see the B is pointing upwards. Huh? This one pointing upwards. That means South Pole is on top. So you have I and you have B. Yeah. Okay. So because of that, the interaction between the B and the I produce a magnetic force. So you have to find out the force by using Fleming left hand rule. So let us put it at the side here. So your current is here. Your B is up. So you have to use Fleming left hand rule again. Okay. Then you will realize that your force is to the left, which is like this. This is called magnetic force, perpendicular to each other. Huh? Okay. So magnetic force. This is Fleming left. Fleming's left hand rule. Okay, so the magnetic force is to the left. Okay, so that's why if you see the picture here, the magnetic force is to the left. Okay, so it means they will push the positive charge to the left. They will put the positive charge to the left. As you can see, positive charge is going to the left already. They will push the positive charge to the left because of the magnetic field. Because of the magnetic field, so it pushed the magnetic charge. The magnetic force pushes the positive charge to the left and making the negative charge on the other side. And this creates electric field. So electric field is where it starts from positive to negative. So electric field has the electric force. So the electric force is positive to negative. Okay, positive to negative. So magnetic force is acting to the left. Electric force is acting to the right. Then after that, what is Hall effect then? So let's see here. The Hall effect is a mechanism in which magnetic and electric forces on a moving charged particle are balanced. Okay, so what are they trying to say is same force, same force. The Fm is equal to Fe. In that case, if the forces are balanced, then that is called Hall effect. That is called Hall effect. So I write at the side first. Hall effect is where the magnetic force is equal to the electric force. Okay, so let's see more information first. Okay, I will explain further. Now you just roughly know about the situation. So let's move on first. The second point. The probe is made of semiconductor material. Okay, semiconductor material. as electrons travel faster in it than metal, and then greater effect. So what are they trying to say about here? So I have to put it in this way, because this second point, right, this second point has a little bit of problem, which confuse us a little bit. Okay, now I have to put it in this way for the second point. Okay, this second point, okay, let's look at the statement down here. If the probe is made of semiconductor, okay, so I put it on the left, semiconductor, compared to metal, because the second point is talking about metal and semiconductor, right? Okay, so first of all, let's see the difference. If you are using semiconductor as the probe, then you have to know that the charge carrier are holes. So what is holes, or what are holes? Holes are positive charge. Okay, so that means positive charge is moving in the semiconductors. Holes are moving. Holes are positive charges. So holes are moving in a semiconductor. So that's why when we look at our picture here, the current is passing through the semiconductor, and in that situation, positive charge is moving in the semiconductor. So positive charge that I mean here is the hole. So the hole, or the positive charge, based on Fleming left-hand rule, experiences magnetic force to the left. So that's why the positive charge moves to the left, and then gather up on the left, and then here become negative charge, because positive charge to the left, so leaving the other side become negative. Imagine that initially the semiconductor is neutral, okay? So because of the magnetic force, so it make here positive, it make the other side negative. Okay, so now let's move on. More informations. Okay, so semiconductor, the charge carriers are holes. So how about metal? So let's compare. For metal, the charge carrier are electron. Okay, so what's the difference? If the charge carriers are holes compared to the metal where the charge carriers are electrons, so is there any difference or not? Of course, yes, there is a difference. Okay, so let us put it in the similar way. Okay, so I draw a probe. Okay, so this probe is made of semiconductor. Okay, now here I draw another probe. This probe is made of metal. So we want to see the difference. Okay, so again the B is pointing upwards, same as our situation here. The B is pointing upward. The I is this way. Okay, so likewise here same, B, and then the I. Okay, So there is a difference actually. So there's a difference. So the difference is like this. For semiconductors, I already explained it. So where if you use Fleming left-hand rule, the magnetic force is this way. The charge carriers are holes. Holes is the positive charge. So it will follow the magnetic force and it makes the positive charge gather up on the left-hand side. Positive charge. So this side become negative. Okay. So if you are using metal, so what happened is the charge carrier are not holes anymore, are electrons. So they are electrons. So electron flow in the opposite way compared to current. So the electrons will move in the opposite way. So which means here, we move in the opposite way. So imagine that electron is moving here. Okay, it's moving there. And based on Fleming left-hand rule again, so there is a magnetic force which act to the left, and the magnetic force pushes the electrons to the left then. Okay, so you have to know something like that. Huh? It push it to the left, so making the left-hand side become negative. And because of that, the other side is positive. And that is the difference. Okay, so if you use metal and you compare to semiconductors, there is a difference because they are using different charge. They are using different charge carriers, and after that, the magnetic force will push the charge carrier to the direction that follow the magnetic force, and it creates electric force. Okay, so electric force, how it acts for this case, for the first case here, for semiconductors, positive to negative. So electric force is this way, electric force, positive to negative. Okay, whereas for the second case, what happened is positive to negative. That means the electric force is from right to the left. Okay, right to the left. Electric force, huh? Right to the left. Okay, now let's move on. Next point. Okay, which is this point, the third point. A small current flows through the probe and a magnetic field is applied. So the electrons are pushed sideways by the magnetic force accumulating on one side, hence producing a small voltage that is called Hall voltage. Okay, so this statement, you have to know this statement is talking about metal, because the charge carrier is electron, then they say the magnetic force push the electrons to the sideway. So this statement will be okay if we are using metals. Then the electrons are pushed sideways, so then it creates Hall voltage. What is Hall voltage then? Hall voltage. So let's take a look. So remember, this third point is for metals. Semiconductors, we don't say this way. We say a small current flow through the probe and a magnetic field is applied, so the holes are pushed sideways by the magnetic force accumulating on one side, hence producing a small voltage, Hall voltage. So for semiconductor, you say holes. For metal, you say electrons. Okay, now Hall voltage. Let's take a look at the picture. So you can measure the Hall voltage by connecting the voltmeter to the positive side and the negative side, then it creates a potential difference that is called Hall voltage. Hall voltage is measured in that particular way. Okay, so we move on. Next point. The greater the flux density, the greater the Hall voltage. So this one, how you'll be able to understand it easily later when you look at this point. So let's take a look. We look at the formula for Hall voltage. Formula for Hall voltage equal to Bi over NTQ. We will look at this later, but now you just try to understand this point. The greater the B, the greater the Hall voltage. Based on the formula, yes, it's true. Okay, it's true. Based on our explanation just now, when we try to understand everything, right? So somehow it should be true also. Imagine if the magnetic flux density is greater, the B is greater, then the magnetic force is greater, then here become more positive, then here become more negative, then the potential difference is greater because this is more positive, this side is more negative, then the Hall voltage is greater. So it is reasonable. Then next one, if magnetic field direction is reverse, so that means you change your B downwards, and then your Fm will act in the opposite direction, which is to the right, and then the positive charge will gather up at this side. If you are using semiconductor, the holes are gathered up here, and then the negative will be the other side, and then the electric force, the electric field will act to the opposite side also. So everything will just at the other side. Okay, so if magnetic field direction is reversed, electrons are pushed to the other side, to the opposite side, and Hall voltage is reversed. So which is true, but you see, they are using electrons to explain the statement. So if they are using electron, that means you have to apply it to metals. So yeah, you have to be careful. These three statements that I put in the box, be careful of it, because it is a bit confusing because you see they are using semiconductor. Then semiconductor supposed to have holes as the charge carrier. Then everything should be reasonable. But if they are talking about electrons, then you have to be careful. Let's take it as hole then. Okay, the semiconductor then hole will experience the magnetic force. Then hole push sideways. Okay, then the holes push to the opposite side, and then the Hall voltage is reversed. Okay, let's change it to hole then. If we are talking about semiconductor, if we are talking about metal, right? So here you change it to metal, then the electron is applicable. Then electrons are pushed sideways, and then electron pushed to the opposite side. So that is for metal. Okay, so now let's see the formula. So we already understand the concept, and now let's see the formula. Okay, so okay, maybe we use some logic to think about it. I'm talking about semiconductor. So semiconductor is where the positive charge is pushed to the left, and if the holes, the positive charge is pushed to the left, then the other side will become negative. That is quite natural. And then the electric force is created in this way. And then they say Hall effect is the magnetic force equal to the electric force. So if the force are same, then what will happen then? That means if the force are same, right? That means if we still have any positive charge in future that passing through the semiconductor, they won't go here anymore. No? If the positive charge want to come here due to the magnetic force, then the positive charge is at the same time pushed to the attracted to the right, because here is negative charge, So as in the Fe here, the electric force will push it to the right because here is negatively charged. So the future positive charge, right? When Fm equal to Fe, right? The positive charge will not go to the left or right, but they will move in straight. They will move in straight. Okay, so when Fm equal to Fe, the positive charge will not go to the left or go to the right, but they will move in straight. Okay, now what is the function of this thing? You see they are saying that this piece of thing is a probe. What is probe? Probe is a detector. It's a detector. It's to detect what? Okay, is to detect how strong is the magnetic field, for example. So that is the function of the probe. Okay, we will see it later in past paper. You will see past paper where they ask about the Hall probe, right? They will put the Hall probe as a probe or a detector that determine uh, the B, for example. Okay, of course there are other usage. So we'll come to that later. Now let's move on. Formula 9.12. The Hall voltage. Okay, so let's take a look. An electric field is set up in the probe as there is a difference in voltage between a distance d. So E equal to VH over D. Okay, so we look at the picture again. Electric field is set up. So because this side is positively charged, the other side is negatively charged. So electric field is positive to negative. And let's come back to the formula. We learned electric field during AS or during A2 chapter 7 as well. So we have to know that electric field, the formula is V over D. V over D, V over D, voltage or potential difference over distance. So electric field equal to potential difference over distance. So the potential difference is the Hall voltage, and then the distance is the D. Okay, let's see what is D again. Okay, so the potential difference is this one, and the distance is here to here. The distance that separate the charges, the positive charge and the negative charge. Okay, so last time during AS physics, we learn E equal to V over D in this scenario. So you have a positive plate, then you have a negative plate, then the separation. So we learn it in that way. This is just similar, This is just similar. The positive charge is at one side, the negative charge at the other side. The distance is the distance that separate the charges. So the electric field is in between. Okay, so now let's move on. Second point. As a single electron travels with drift velocity v, it experiences a force to the left. Okay, we have to change this as we have discussed. Let's see. Okay, here. As a single electron travel with drift velocity v. So when I talk about electron, okay, so electrons experiences a force to the left. Okay, it's for metal, yes, to the left. For metal, yes, to the left, due to the magnetic field. Okay, so the force is PQV. Okay, let's see the point again. Okay, so that means this second point, as a single electron travel with drift velocity v, it experiences a force to the left due to the magnetic field. Okay, so this statement is for metal as the probe. Metal as the probe, then it experiences force to the left. Okay, so the magnetic force is BQV. Magnetic force is BQV. Okay, so this BQV is magnetic force experienced by the electrons. That is BQV. And a force to the right due to the electric field. Okay, let's see the diagram again. Electric field is to the right. Okay, so yeah, true also, but it is for metal as the probe. Electric field is to the right. Is it? Hold on, electric field. Okay, let's see first. And a force to the right due to the electric field. EQ. EQ. Positive to negative. EQ. Okay, so some problem here. Okay. Electric force is to the left for metal. Okay, so that statement again, having a small problem. I put a box first because they mix up everything and put together, So we have to make it as clear as possible. So I put a box here, meaning that this sentence need to be careful. Our probe can be semiconductor or metal. Okay, so to make everything make sense here, so let us put it as semiconductor then. Semiconductor. Okay, so if I put it as semiconductor, we need to change a little bit. As a whole travel with drift velocity v, it experiences a force to the left. Okay, I change it to whole then. Okay, I change it to whole. As a single whole travels with drift velocity v, it experiences a force to the left. So then it makes sense already. Yeah, the whole move to the left due to the magnetic field. Then it has magnetic force PQV, and the force to the right. A force to the right is the electric force, as you can see in the picture. Okay, due to the electric field, EQ. EQ. How we get EQ? So be careful with this. We learn it in AS physics, where electric field equal to V over D equal to F over Q. Okay, so we take this and this, then we get F equal to EQ, the electric field. Electric field. Okay, so they are trying to apply Hall effect. It's just that the statement is confusing between the semiconductor probe or the metal probe, So I have to adjust it until it makes sense, yeah. So now they are trying to say the Hall effect, Fm equal to Fe, Fm equal to Fe. So at that time, right, we can equal the two forces here. The magnetic force, the Fm, is BQV. The electric force is EQ. So the two forces are equal to each other. So we get this equation. And after that, once you get this equation, then you can substitute E equal to V over D, right? You substitute over here. So that's why you can see the next point. The E is replaced by VH over D. The Q is from here, still remain. Right hand side remain the same. Okay, so then we get this equation. And let's see the next point. Current is related to mean drift velocity. So drift velocity by I equal to NAVQ. I equal to NAVQ. Okay, so this is the formula that contains the drift velocity, how fast the positive charge in the electric field. So that is the drift velocity. So the V is there. So I equal to NAVQ, and after that, what is A then? What is A? So we have to take A as T times D. As you can see, A is T times D. So let's look at the picture first. What is T times D? So T times D is, if you see the picture, T times D is here. Okay, here. What is so special about this? This is the area, the cross-sectional area where the current enter and come out. Okay, so it enter to that particular area, and it come out from that particular area. So we use that as our area. So that's why A equal to TD. So where it is the cross sectional area where the current enter or come out, and N is the number density of conducting particles. So maybe you are confusing a bit. What is this? Number density of conducting particles. Okay, so if you can't take that, I have another version for you. You can also take N as mobile charge carriers per unit volume. So mobile charge carriers per unit volume. That means how many mobile charge carrier, how many moving charge per unit volume, per meter cube, for example. So basically N means that. Okay, so easier to understand. If you take number density is already something which is a bit hard, but number density means number divided by volume. Okay, number divided by volume. You have to take it in that way. Number divided by volume. It's not the normal density. Normal density that we normally heard is mass divided by volume. Number density is number divided by volume. So that's why if you can't remember number density, then you take this number of mobile charge carriers per unit volume. So it's number divided by volume. So that is the N. Okay, so which is this N. Okay, now what we do is let's see the next page. We find out the V from this equation. So let's do it at the side here. V, the drift velocity, equal to I over N A Q. The A, the capital A, I change it to TD. N T D Q. Okay, so I get this. I get the drift velocity. Then I'm going to substitute the drift velocity. Substitute the drift velocity to here. And after that, After substitute, then you will get this then. Okay, so let's continue. Left hand side, QVH over D, same. That is left hand side. Right hand side, BQ, BQ you can see, the V has been replaced by I over NTDQ. As you can see, I over NTDQ. So after doing so, now they simplified it. First, they cut the Q on the numerator and the denominator. Then they cut the D on both sides. Then at the end, they get BH equal to BI over NTQ. Okay, so this is the formula then. This is the formula for Hall voltage. Okay, so now when you know the formula for Hall voltage, so we need to know some relationship here. The first thing, if the I is bigger, the Hall voltage should be bigger. That is the first thing. Logically, it is true, because if you use a greater I, so let's look at the picture here. If your I is greater, this I, if the I is greater, then they will have more charge carrier that go to the left, and then making here more positive, making the other side more negative, then the potential difference, the Hall voltage is greater. So logically this is true. And the second thing is if the B is greater, then the VH is greater also. So again, it is the same reason, because of greater magnetic force. Greater magnetic force that push it to the left, making the Hall voltage greater. Okay, so at the end, I'm going to put Hall voltage settled already, but we have to do question also. Before that, I just put it in this way. Hall voltage is exploited in instruments called Hall probes. Probe means detector. So this is a detector which are used to measure magnetic field strength or magnetic flux density, which is B. So the probe is used to get the Hall voltage, and then through some system or through some calculation in the computer, then they will tell you how much is your B. How they will tell you the value of your B. Okay, so that means at the end, we use Hall probe to measure B. Okay, and how they measure B? They measure VH first, Hall voltage first. They measure Hall voltage, then after that, the computer will do calculation for you, and at the end, you will get your B. You will get the value of B. Okay, so that is Hall probe. Okay, so let's finish everything here first before we look at the questions about Hall probe or Hall effect. So 9.13, deflections of electrons through magnetic field. So they use B field. B field means magnetic field. Okay, so it will be circular motions. Okay, circular motion. So circular path. Kinetic energy is constant. That means the velocity. The velocity is constant. Okay, so velocity is constant. We already explained in the past year question before this, where they say the force is perpendicular to the velocity. So this tangent direction experience no acceleration. So that's why the velocity is the same. So if same velocity, then same kinetic energy. Okay, then the force is perpendicular, right? That is what we call the centripetal force. So that's why the magnetic force BQV is equal to the centripetal force mv squared over r. So when they are equal, then you can just rearrange it. How you rearrange? Imagine you can cut the V on both sides, and then you bring the R to the left, make R as the subject, yeah, and then here BQ you bring it down to the denominator, and then you get R equal to MV over BQ. So you get this relationship. Okay, so the R is the radius, and then we can see some relationship here. Faster moving particles move in bigger circles. R is proportional to B. Reasonable also because you see the equation. If the velocity is greater, then the R is greater, provided that your mass, the mass of the charge, the mass of the moving particles, and the B, the magnetic field strength or the magnetic flux density, and the Q, the charge of the moving particles, provided that these three are constant, then we can say that R is proportional to V. Okay, R is proportional to V, yeah. So if R is proportional to V, right, then we can get something, we can get something like this. Okay, I put it at the side first. R is proportional to V. That means R over V is a constant. What constant is that? Imagine R divided by V. This V you bring down. The constant is M over BQ. This constant is M over BQ. This constant is M over BQ. Okay, so then because of that, we can create this formula R1 V1 equal to R2 V2. This formula is sometimes useful to find out the velocity easily. Okay, so that means if the radius is a particular value, then the velocity should be another value. Okay, so if the radius is a greater value, then you should expect the velocity should be a greater value also. You can use this formula to find out. Okay, next one. Heavier particle move in bigger circles are proportional to m. So, meaning that this should be reasonable also. R, m. If R is bigger, if m is bigger, then R is bigger. So logically, this is true also. Okay, so if you look at the equation that I circle in blue, logically that is true also. So again, when you want to put it in this way, which is proportional, and then you have to assume the rest are constant, the V, the B, and the Q are constant, and then they are proportional. And if they are proportional, okay, let's take a look here in blue color. If R is proportional to M, that means R over M is a constant. And what constant is that? So R over M, you can see the equation here. You bring the M down. So the V over BQ is the constant. Okay, so I write down V over BQ is the constant. And then you can create formula. R1 M1 equal to R2 over M2. So you can create formula and apply accordingly. Okay, then meaning that you can find out the mass of the particles when the radius is a particular value. Now, last application, the stronger field, particle move in smaller circle. Okay, so logically this is true also. As you see green color, if the B is strong, then the R should be small because B stay at the denominator. So in that case, we will have R inversely proportional to B. And if this is the case, again, we can do something similar. R times B is equal to a constant. So what constant is that? Imagine you look at this formula, you bring the B over here, R times B is mv over q. So the constant is mv over q. Then we will get R1 B1 equal to R2 B2. So we can get this relationship. So a lot of application here. So you can find it in past paper lah. Okay, so let us look at the question that related to the Hall probe or the Hall voltage. So yeah, a thin rectangular slice of aluminium has sides of length 65, 50, and 0.10 mm as shown in figure 9.1. Some of the corners of the slice are labeled. A current I of 3.8 ampere is normal to phase RS XY. So you can see the picture of the slice. In aluminium, the number of free electrons per unit metals per unit volume is 6.0 times 10 to the power of 28. Okay, so this value is n. This value is n. If we still remember, n is called the number density, number density or number of charge carrier per unit volume. That is number density. So this is the one, number of free electron per unit volume. Why this is free electrons here? Because this is a metal, This is aluminium. Aluminium, the charge carrier is electrons. So that's why they're talking about electrons here. Okay, we move on. This point, a uniform magnetic field of magnetic flux density B equal to 0.13 Tesla. And they give us B. Okay, we label it first. This is B. It's normal to phase Q, R, Y, Z of the aluminum slice in the directions from Q to P. Okay, so you can see the pictures, the magnetic field. And then a Hall voltage VH is developed across the slice and is given by the expressions VH equal to BI over NTQ. Okay, so VH equal to BI over NTQ is actually the formula that we derived just now in the notes. Okay, now let's move on. Okay. A. Use figure 9.1 to state the magnitude of the distance t. Magnitude of the distance t. Yeah. Okay, so the probe has been turned in a particular way already. You have to be very careful. Where is t? Okay, where is t? Yeah. So first of all, you need to remember where is A first. A is this one. The current enter the surface. That is the A. A equal to TD, right? A equal to TD. The which one is T and which one is D, right? So if you still remember the note just now, D is the one that represent the distance of the positive and negative charges. Okay, so where? let's use Fleming left hand rule. You know B is downwards. You know current is to the left. Okay, so if you use Fleming left hand rule, so you will realize the force is coming out of the screen. This way. The force. Fleming left hand rule showing that the force is coming out of the screen. So this is the magnetic force. The magnetic force will push the charge carrier out of the screen. So for our case, it is the electrons. The charge carrier for metal is electron. So electron will come here because the magnetic force is here. Okay. The positive charge will be there. What is D? So D is the distance of the positive and negative charges. So which is here to here. D is this one. So this is D. This is D. Then what is T then? T is the one that contribute to the cross-sectional area. So you know this area, right, is D multiplied with T. So this is automatically the T. So I write it down. That is the T. Okay. So now they ask you to state the value of T. So it is 0.10 mm. Okay. B. Calculate the magnitude of the Hall voltage VH. So we just use the formula. This is the formula given. We substitute value only. So VH equal to B. The B is 0.13 Tesla. The I, current 3.8 over the N. N is the number density, which is number divided by volume. And then after that, the T, the thickness, 0.1 mm, right? SI unit, 0.10 times 10 negative 3. And then followed by Q, the charge. The charge of, the charge carrier here is electrons. The charge of electrons, you can see the data booklet, 1.60 times 10 to the power of negative 19. Okay, then you press calculator, then you will get 5.15 times 10 to the power of negative 7. Then we write the answer here. Okay, so this is a question related to the Hall voltage. This is the simple one actually because the formula is given also, So let's see the next one, right hand side. Okay, so a magnetic field of flux density B is normal to phase PQRS of a slice of a conducting material as shown in figure 9.1. Then a current I is in the slice is normal to phase QRZY of the slice. The Hall voltage VH across the slice is given by the expressions VH equal to that. A part 1, state what is represented by the symbol N. So the symbol N is number of charge carriers per unit volume. Okay, so of course, if you don't feel like using this, you can say number density. Number density of charge carriers. Okay, and then the charge carrier you can replace with free electrons also, because the charge carrier for conducting material, which means metal, is free electrons. Okay, you can replace with that also. And then part 2, the symbol T. So this one we discussed already, as you know, D is like this, T is here. So where it make up the area that the current enter. So T is RZ or PX or QY, whichever lah, no? So let's say I just put RZ, okay, RZ or QY or PX, three options. So B part 1, in general, the Hall voltage produced in a slice of a metal is very small. For a slice of the same dimension with the same current and magnetic flux density, the Hall voltage produced in a semiconductor materials is much larger. Suggest and explain why. So you know, initially they are using metal. Okay, now they change it to semiconductor. Okay, the probe they change to semiconductor. So they want you to explain, suggest and explain. Okay, so how to explain? You can use the formula here. The formula. Okay, so how to use? You know, semiconductors has less number of charge carriers. This is small, and then this is big. Okay, so that is what happened to the semiconductors. Okay, so we write down VH is inversely proportional to N for, okay, this is the first point. Okay, second point, for semiconductors, N is much smaller than for metals. Okay, so this one settled already. Okay, the questions. In some semiconducting materials, electrons are mainly responsible for conduction. In other semiconducting materials, holes are mainly responsible for conduction. Suggest and explain the difference, if any, that conductions by electrons or by hole will have on the Hall voltage. Okay, so let's see. They say they have different charge carrier here. Okay, so first, magnetic field would deflect holes and electrons in same direction. By using Fleming's left hand rule. Okay, this is the first point. So you know, we use Fleming left hand rule to find the Fm. The Fm will push the holes, or will push the electrons to the direction that follow the Fm. Okay, so then next point, because electron is negatively charged and hole is positively charged. Third point, VH has opposite polarity. So these are the effect. Okay, so settle. Okay, 9.14, charge to mass ratio. Okay, so first point, the charge to mass ratio is known as the specific charge on the electron. Okay, so which means you take the charge of the electron divide by the mass of the electrons. So you have to divide that, then you get the charge to mass ratio. Okay, so of course, that is uh, the value we know actually. If you look at the data booklet, you will know about the charge of the electron, which is 1.60 times 10 to the power of negative 19. Yeah, we know this. The mass we know. We know that the mass of the electron is 9.11 times 10 to the power of negative 31. So from the data booklet, we know the range, the values. So if you divide, then you get already. But the thing is, over here, they want you to derive it. Okay, so let's see. This point, work done by electron is equivalent to kinetic energy it possesses. It possesses. Okay, so that means work done by electrons, W equal to QV. W equal to QV. Yeah? Okay, so where is this formula coming from? Of course, we discussed this before. We discussed something like this. The definitions of potential difference is the work done per unit charge. Work done per unit charge. Then you rearrange the formula. Then you will get this equation. W equal to QV. Okay, so our Q here is the charge of the electron. So that's why they're replaced with E. Q equal to E. Okay, so the kinetic energy is 1 over 2 mv squared. And we take the work done equal to the kinetic energy. Okay, so how much work is done by the electrons affect the kinetic energy. Okay, so that's why we can equal to each other. And then we continue. Next point, using equation for an electron traveling in a circle in a magnetic field to eliminate V. That means what? That means just now, right, when we learn this thing, we have end up with a formula which is R equal to mv over bq. So we have this formula. Okay, so over here, the q, the charge, is replaced by small letter e. Small letter e. The m, right, is replaced by me, the mass of electron. So we change this to me then. Me v. Okay. Now you rearrange it. So you rearrange it, then you will get v equal to, let's say I want to find v in terms of other lah. So RBE over ME. Okay, then we get this equation, and we substitute this equation into here. Okay, substitute over there, then you can see this part changes already. The rest remain the same, as you can compare with this one. Remain the same, and the v is substituted by this, then you have to square it, and then when you square it, then of course imagine let us do it step by step. Let's skip all the step already. EV equal to 1 over 2 m. Okay, so we need more space. Okay, EV equal to 1 over 2 me r square b square e square over me square. So we square everything. Okay. Then after that, we can cut the ME here and here. Then we can cut the E on both sides also. Okay. Then after that, we can rearrange it. Okay. So we can rearrange how to rearrange. What we want is we want E over ME. We want the charge over the mass. Charge over the mass. So as you can see, the charge is on the right, the mass is on the right also. Then we can shift everything to we can shift the remaining thing to the left. So 2v over r squared b squared. Then after that, we get this formula. So this is the formula. So try to find out, try to understand the way to derive it, because sometimes the question asks you to derive it. Okay, so these two are the important formula. And now let's move on. 9.15, deflections of electrons through electric field. Okay, so you can see here, if the electron is moving through the electric field, okay, so that will go down. Why? Because the bottom is positive charge. Electron is attracted by the positive charge. Okay, so how to do calculation then? So you can see here, determining the motion of the electrons. So we use S equal to UT plus half AT square, and initial vertical velocity equal to 0 meter per second. So that means we applied this formula in vertical direction. Vertical direction. That means the S is how much it moves in the y direction, in the vertical direction. That means it's y. As you can see, they are using y to represent the vertical distance. So the S is replaced by the S here is replaced by y. The U is 0 because vertically it is not going down at the beginning. It will go down after a while. Initially it is not going down. Okay, so that's why U equal to 0, okay, which is this value. You substitute here, and the UT terms gone already. Only half AT square remain. So that's why we have this half AT square. And after that, let's move on. The other side. Okay, so finding an equation for accelerations. Okay, so first, what they use is they use F equal to QE. Where is this formula coming from? Let's do a quick revision. So we know electric field equal to V over D equal to F over Q. So they are using E equal to F over Q, then they rearrange, then they get F equal to QE. F equal to QE. So again, for electron, the Q is equal to E. Okay, E. And then after that, Newton's second law, we have F equal to ma. Okay, so after that, imagine you rearrange the F equal to ma, you get A equal to F over m. And then you substitute F equal to QE to the numerator. That's why the top become EE over m. So we get the acceleration. Okay, we get the acceleration. Okay, now as particle moving horizontally at constant velocity and time is the same for the whole journey. Okay, so it means what? So let's see the screen. Let's see this side again. Horizontally, it has no acceleration. And horizontally, the time it takes to reach from here to here, to this point line, from here to this point, is the same with the vertical. The vertical means the time it takes from here to reach y. Okay, so maybe I draw it out. Horizontally, the time span from here to here is t. Vertically, the time span from here to here is also t. It has the same timing. Okay, so it has the same timing for the particles to travel from here to here horizontally, or vertically to travel from this point to this point. We take the same timing. Okay, so that is what are they trying to say. And because there is no acceleration, so we use the formula s equal to ut plus half at square, and then because there is no acceleration, this is 0, and because of that we will have this term disappear, this whole term disappear, only the s equal to ut remain. So the u is replaced by v, as the, you see the picture again, they are using v, they are using v as the initial horizontal velocity. So that's why they replaced by vi supposed to be vi if you follow this picture. Then the t is the time it takes from here to here. Okay, then after that, the t that they rearrange this equation, then they get t equal to x over v, and they substitute the two equations here, a equal to e over m and t equal to xv. So they substitute these two equations, this equation and this equation, into our result just now. Our result just now on the left bottom page is y equal to half at square. They substitute it here. So imagine this one, they substitute here, and t they substitute here, then end up with this result. Okay, this result. So this result is power 2. It's a power 2. It's a quadratic equation. So it's a quadratic equation. That's why you should expect this is a parabola. This is a parabola, quadratic, right? Okay. So hence y is proportional to x squared, therefore parabolic or projectile motion. Gain in y components of velocity, kinetic energy increases. So that means in terms of vertical direction, right, the velocity is increasing, so kinetic energy is increasing. That is for vertical component. So let us look at 9.16 now, cross fields. So first point, considering a setup where electric and magnetic field are perpendicular to each other and act on a moving charge simultaneously. Okay, so which means you have electric field. Okay, you have electric field as in the diagram here, positive terminal, negative terminal. So the electric field is where it goes down from positive to negative. We follow the blue arrow. Magnetic field are perpendicular to electric field. As you can see, the purple one, they put a cross here. So with B, that means the magnetic field is going into the screen, and going into the screen means the north pole is away from the screen, and then the south pole is at the other side of the screen, inside the screen. Okay, so it's north pole to south pole. Okay, so that is the electric field. And then you have a charge. Okay, you have a moving charge. So you have a moving charge with a particular velocity. So there will have three situations here. if the the moving charge is a negative charge as is written here. So the first situation is where they will move in straight line. So it moves in straight line when the electric force is equal to the magnetic force, and then it's moving in straight line. Of course, at the meantime, you have to know the direction of the electric force and the direction of the magnetic force. So, for example, if this is a negative charge, so of course the electric force will make the negative moving charge to the positive terminal. So we should expect electric force should act upwards. Electric force should act upwards as opposite charge attract each other. So negative moving charge is experiencing electric force which act upwards, which is making it to the positive terminal. But the magnetic force, you have to use Fleming left-hand rule to decide. So to use Fleming left-hand rule, so we have to consider the three things, the B, I mean the FBI lah, basically, yeah. Okay, so let's say the F. Okay, F maybe we consider later. We consider the B first. The B is going into the screen. So imagine it's going to the screen, and then I is to the right. I is to the right, and then you use Fleming left-hand rule. So your index finger point into the screen, your current point to the left. So you will realize your force is pointing downward. Your force is pointing downward. Your magnetic force is pointing downward. So must be perpendicular to each other. Okay, so from here, it will be clear that if the electric force is equal to the magnetic force, then they will move in straight line. Okay, so V equal to E over B. Why is it like that? Of course, there are proving there, so we'll take a look later. But we look at the green color one first. The green color happens when the electric force is greater than the magnetic force. And the yellow color, it happens when the magnetic force is greater than the electric force. Okay, so logically it should be like that. Now let us see how they get E over B. So we look at the second point. In such case, a certain velocity exists where fields exert equal and opposite forces. So that means we have magnetic force because of the B field, and we have electric force because of the E field. The magnetic force formula is BQV. This is the formula for magnetic force for a moving charge, BQV. Electric force, the formula is QE. QE must remember lah, must memorize. Electric force is QE. Then we cut the Q on both sides. Try to imagine that. Cut the Q on both sides. And then we want to find V in terms of the rest. So as you can see, V remain here. B bring down to the denominator, and we get E over B. So we will get V equal to E over B when the electric force and the magnetic force are equal to each other. Then you will get same. So in what situation you will get V less than E over B or V greater than E over B? Yeah? So you can see here, if velocity is higher, that means the moving charge is moving faster, then the velocity will affect the magnetic force. So F equal to BQV, you see the V is there, so it affects the magnetic force. Hence, magnetic force is stronger, and effect of force due to electric field decreases. So that means you have a greater magnetic force, so making it having a downward motions. Okay, so because magnetic force is greater, and magnetic force is greater because the velocity of the moving charge is greater. So basically, it is related in that way. So velocity is, okay, let me make a conclusion like this. Velocity is higher, magnetic force is greater than electric force, then move downward. Okay, so when we come to the formula, so basically what happened is, let's say I follow their color, I put in yellow. So what to do is, our B field is more than the E field. So BQV is more than QE, and then V is more than E over B. So basically, you just need to change the equal to more than all the way, then you will get V greater than E over B. So next point, the last point here, if velocity is lower, smaller V, so F equal to BQV. So the magnetic force, of course, is going to be smaller, and hence magnetic force is weaker, and effect of force due to electric field is increases. So meaning that, okay, so they are trying to say, just now I should put, just now when the V is greater, now when V is lower, then the magnetic force is smaller than electric force, then it will move up, and everything is just the other way around. I use green color, so this is less than, the magnetic force is smaller than the electric force, so BQV is smaller than QE, V is smaller than E over B. Okay, so it works in this way, and let's move on. Okay, this is the last subtopic, which is the comparisons between the gravitational field, electric field, and magnetic field. Okay, they are related somehow, so we need to know how is it. So we start with gravitational. So they say force is always attractive, so always attractive, and electric field, force is attractive or repulsive. Okay, a quick revision. So electric field, if they have the same charge, then they will repel. If they have the opposite charge, one positive and one negative, then they will attract. Magnetic field, the magnetic force is going to be attractive if it is north pole with south pole, and if the magnetic force is repulsive, it happens when you have like poles that come nearer to each other, like north and north or south and south. Okay, so let's look at the next point. Force directly proportional to the mass. So force directly proportional to the mass. Okay, so we put the formula at the side as revision. Okay, so we have to know, for gravitational force, F equal to G M M over R squared. So if you still remember the gravitation law of Newton law of gravitation, so they said the force is directly proportional to the product of the masses and inversely proportional to the square of the distance between the two masses. So that formula. Electric field. Okay, so they said force is directly proportional to the charge. So what formula? So let's say I put it here. Force is QE. QE, charge charge multiply with electric field strength. So that's why directly proportional to the charge, as the electric field strength is constant. And next one, magnetic force. Force is directly proportional to the current. Force is directly proportional to the current. So formula, F equal to F equal to BQV, or F equal to BIL sine theta. So we have two options. Okay. So if you look at the second one, then we know that it is proportional to the current. Okay. So I left out one formula for electric force. So for electric force, we have another one. So let us pull it up here. Beside F equal to QE, so we have F equal to QQ over 4 pi epsilon naught R squared. So we have this as well. Okay, so this is another option where you will realize that it is equal to the multiplication of the charges and inversely proportional, I mean directly proportional to the product of the charges and inversely proportional to the distance between the charges. So you will realize that this and this are the same or similar format. Okay, they have the similar format. And okay, let's move on. Okay, this one. Okay, so or maybe I can give one more situation for the magnetic force. So magnetic force, right? We have one more situation also. Although this formula is not that formal, but it come out in past year paper. So we have force equal to mu naught I1 I2 times L over 2 pi d. Okay, so we have this also. Although this formula is not so formal, but it come out in past year paper. So I put a small note here. This is on my page 4 of the notes. Okay, so the reason that I put this is because I want you to know that, there are similar format. Gravitational force, product of mass over r square. So electric force, product of charges over r square. And then magnetic force, product of current. We don't have r square at the bottom, but it is still okay. Okay, so we at least we see something. We have product of current. Product of current. Okay, so the first two are the important one, and the third one is just for the two straight wires with current. Okay, so I have to be careful with the third one. Okay, so the third one is just for extra reference only. Now let's move on. Force is inversely proportional to square of the distance. So as you can see, we have r square for this case. We have r square also for this case. And this one we have also, even for magnetic force. Magnetic force, we have a particular formula also, where there is r square at the bottom. Okay, so that means for the magnetic force, the formula with r square at the bottom is too complicated, and hence it is not in the syllabus. Okay, so we don't want to care about that formula. Okay, the formula is too complicated. But you just remember the fact it is inversely proportional to square of the distance. This is a true statement for three of these fields. Okay, now we look at the next information. So the next information, they said force independent of the medium. So that means it works in vacuum also. Okay, it works in vacuum as well as the normal surrounding. So as in the attraction between the sun and the earth. Okay, so it's independent of the medium. And electric force and magnetic force. Force depends on the medium. So how? So for example, okay, example, insulator can weaken electric field. Okay, so this is one example. Second example, soft iron core can strengthen magnetic field. So you see the medium affect the electric force and the magnetic force. Okay, next one. Gravitational force. Force is weak. Force is weak. Electric force. Force is strong. Then magnetic force. Force is strong. Okay, in general, it's like that, you know. But you may heard of in the outer space there is a black hole where the gravitational force is very strong. It's so strong that until light cannot come out. So it can be very strong also, you know. Gravitational force can be very strong also. But let's say we put it in general. Force is weak. Okay, so now next one. Force is in direction of field. Okay, so it means they follow the directions of field. Okay, so let's compare with this first. Force is parallel to the field, parallel to the electric field. Okay, so force is perpendicular to the field. So force is perpendicular to the field. Okay, so let's see how is this three statement works over here. So the first one, force is in directions of field. So let's say we do a quick revision here. You have the sun and the earth. Okay, this is the sun and this is the earth. Okay, so the gravitational field is like that, which attract each other. Okay, attract each other. So the gravitational force is in the direction of the field. So where the sun is attracted to the earth is attracted to the sun. So it's in the direction of the field. Okay, so this one, force is parallel to the field. So let's say example, you have electric field. Here positive and here negative. So the electric field is down. Okay, if you have a moving charge, negative charge that move here, then the electric field is either, the electric force is either going up or going down. Depends on the charge of the moving charge. So this is a negative charge. So the electric force is hence acting upwards. So we call this parallel to the field. Which two are parallel? The electric force and the electric field are parallel. Sometimes they are same direction, sometimes they are opposite direction. So that's why we just call it parallel. Just call it parallel. Not like this, you know. This one is always the same direction. If the gravitational field is to the earth, and then the force is to the right. If the earth experience attraction force to the sun, then the gravitational field is this way, then the gravitational force is this way also. So they follow the field. Okay, so that means it is like the gravitational force experienced by the sun follow the gravitational field, which is to the right, and then the Earth gravitational field follow the gravitational force follow the gravitational field, which is to the left. So they attract each other in that way. Okay, so whereas the magnetic field, force is perpendicular to the field. Force is perpendicular to the field. So you can understand this by considering Fleming left hand rule. Fleming's left hand rule, where the force is perpendicular to the B, which is the magnetic field, and it is also perpendicular to the current, which is I. So force is perpendicular to the field then. Okay, so next one, the last row. Force is independent of states of motion of the body. As you can see, our formula is a formula without velocity. So as in gravitational force, as you can see, F equal to gmm over r squared, no velocity. Okay, and likewise, electric field, F equal to qq over 4 pi epsilon naught r squared, or F equal to qe, there is no velocity. But magnetic field is different. Magnetic field, they said force is directly proportional to the velocity of the moving charge or the body. Okay, so where F equal to bqv, this v is velocity. So that means the velocity affect the magnetic force. Okay, so now let's look at the questions. A small mass is placed in the field of force that is either electric or magnetic or gravitational. Okay, so you have three possible fields. State the nature of the field of force when the mass is, number one, charge, and force is opposite to direction of the field. Okay, it is charge. Okay, it is charge. The mass is charged. It's a charge. It's a charge particle, and charge particle as in here. Force is opposite to the direction of the field. So this is the example. The field is downward. The electric force is upward. So that is opposite. So it happens to electric field. Yeah, happens to electric field. Electric field it is possible to have the electric force in the opposite direction of the electric field. It is possible. Okay, so that's why the answer is electric field. Number two, uncharged. Uncharged. So when it's uncharged, right? So that means no Q. No Q. And force is in the direction of the field. This one, gravitational field. As in what I explained. So the gravitational field is to the left, and then the gravitational force is to the left. They are in the same directions. And uncharged is, gravitational force is affected by the mass. It's not affected by the charge. So then who is affected by the charge? So if you look at the formula again, you will realize that electric field is affected by the charge. That's why the formula has Q. Magnetic force is affected by the charge also. That's why the formula has Q over there. Okay, so both the electric field and magnetic field is affected by the charge. But gravitational force, no. Gravitational force, you see the formula, is affected by the masses. Okay, now let's move on. The third one. Okay, number 3. Charge and there is a force only when mass is moving. So mass is moving, that means velocity. So like what we discussed just now, the only force that is affected by velocity is the magnetic field. Because F equal to BQV. So that's why this answer is magnetic field. Okay? F equal to BQV. The V is the velocity. So it is for a moving particle with charge at the same time. So it will affect it will have magnetic force. Okay. Now next one. Charge and there is no force on the mass when it is stationary or moving in a particular direction. Okay, so that means what? Okay, imagine that it is a charged particle and that charged particle has no force when the mass is stationary. Okay, when the mass is stationary. So imagine that F equal to BQV. F equal to BQV. So it has charge, so Q. And the force is no force when the particle is in stationary. That means they are trying to say when V equal to 0, then the F is equal to 0. So this is magnetic force. Okay. Or moving in a particular direction. So which means what? That means it is charged and there is no force when it is moving in a particular direction. In what direction that we have no force, for example, you consider Fleming left-hand rule, right? So that we have force when it is perpendicular. It will experience maximum force. Okay, when the directions of the particles, the motion of the particle is in perpendicular with the magnetic field, then it will experience maximum force. But if they are in parallel with the magnetic field, if the motion and the magnetic field is in the same direction or opposite direction, then they will have no magnetic force. So meaning that when they are moving in a particular direction, like parallel to the magnetic field, then there is no magnetic force. So the formula is like this. F equal to BQV sine theta. Sine theta for a more general situation. So when they are moving in a particular direction, like 0 degree, okay. So something like this, 0 degree. So this is the North Pole. This is the South Pole. Okay. So the magnetic field is like this. So the particle is moving in this particular way. The charged particle is moving in this particular way. So if the theta is 0, if theta is 0, that means the particle is moving in the opposite direction from down to up. In that case, theta equal to 0, right? So it will have no magnetic force. Okay, so they are trying to say it in that way. Okay, so this one I put in green. So when theta equal to 0, so you should expect F equal to 0. So it happens to magnetic field. Okay, so settle for this chapter.